Hello, I'm Professor Sid Morris, the author of the online book Topology Without Tears, which is freely available at www.topologywithouttears.net. This is the third in a series of videos on writing proofs in mathematics, and it supplements my book Topology Without Tears. In the first two videos on writing proofs in mathematics, I explained how the notion of a proof in mathematics differs greatly from that in use in everyday discussion, or in law, or in science. Proof has a very particular meaning in mathematics. So before you watch this video, you should watch the first two videos in the series on writing proofs in mathematics. In those two videos, I explained how you should start every proof. After watching those videos, you should never again say, "I do not know how to start the proof." In this video, I discuss a method of proof often called proof by contradiction. It is a very important method of proof. I shall give you some examples of using this method of proof and how you make very clear to the reader that you are using proof by contradiction. While proof by contradiction is a very important method for you to know, it is also important for me to point out the limitations on proof by contradiction, and even why other methods of proof are preferred by some mathematicians and some logicians. So without further ado, let us give an example of a proof by contradiction. The example I will use dates back over 2,000 years to Euclid and is a very small variation of the method that Euclid used. We shall prove that the set of all prime numbers is infinite. We begin in the usual way, and that is writing down what we are given and writing down the definition of any technical term in what we're given. So we're given the set P of all prime numbers, and we recall that a positive integer is said to be a prime number if it has precisely two factors, that is, two distinct numbers that divide it. Incidentally, this shows you that the number 1 is not a prime number. Next, we write down what we are required to prove and the definition of any technical term in what we are required to prove. We are required to prove in this problem that the set P is infinite. We decide to use the method of proof by contradiction. So we suppose that what we are required to prove is not true. That is, in this problem, we suppose that the set P is finite. That is, P equals P1, P2, up to Pn. What we have to do next is not at all obvious. The strategy, however, is clear. We have supposed that some result is true. We now wish to deduce from that supposition a result which we know to be false, and thereby have a contradiction and deduce that our supposition must be wrong. Now we supposed that the set P is finite, that is, P equals P1 up to Pn. We now consider the positive integer n, which is P1 times P2 times P3 up to Pn plus 1. Every integer greater than 1 is divisible by some prime number P. So the number n must be divisible by some prime number P. But n divided by any of the prime numbers P1, P2, P3 up to Pn clearly leaves a remainder of 1. So n is not divisible by any of the prime numbers P1, P2 up to Pn. That is, n is not divisible by any prime number in our set P of all prime numbers. This is a contradiction, as every number greater than 1 must be divisible by a prime number. Therefore, our supposition that the finite set P is the set of all prime numbers is false. Hence, P is not a finite set, and so P is indeed an infinite set, which was what we were required to prove. So you have now seen what is involved in writing a proof by contradiction. You start the proof in exactly the same way as you start every proof. You write down carefully the information that you are given. You write down the definition of any technical terms in what you are given. You write down what you have to prove. And then you write down the definition of any technical term in what you have to prove. When you decide that you will use the method proof by contradiction, you tell yourself and the reader that you are using this method by beginning with the word suppose. Suppose is the clue to tell you and the reader that you are doing proof by contradiction. At the end of a proof by contradiction, you should now say which contradicts what we are given. Therefore, our supposition is false. It is important at the end of a proof to say that you have a contradiction and therefore that the supposition is false. That explains to you and to the reader that the method of proof by contradiction has been completed. Let us now look at another example. In this example, we are required to prove that the set Z of all integers is not an open set in the set R of all real numbers with the Euclidean topology. As usual, we begin by writing down what we are given. We are given the sets Z and R and the Euclidean topology on R. Next, we write down the definition of any technical term in what we are given. So the Euclidean topology on R has a basis consisting of all open intervals A, B, where A and B are in R and A is less than B. And every open set in the Euclidean topology is then a union of open intervals AB. Next, we write down what we are required to prove. Here, we are required to prove that Z is not an open set in this topology. We shall use proof by contradiction. As usual, we begin by supposing the negation of what we are asked to prove. So we suppose that Z is an open set in R with the Euclidean topology. Our aim, of course, is to show that this supposition is false by arriving at a contradiction. We supposed that Z is an open set, and we know that the open intervals AB form a basis for the Euclidean topology on R, so we get that Z is a union of open intervals AB. If Z is a union of open intervals AB, it is certainly the case that Z must contain an open interval AB for some A and B in R with A less than B. Of course, Z does not contain any interval AB with A less than B. There are many ways to verify this. For example, Z is a countable set, while the interval AB is an uncountable set, and no countable set contains an uncountable set. Another way is to say that every interval AB must contain a non-integer rational number, but Z, of course, only contains integers. A third way is to say that every interval AB must contain an irrational number, and Z contains no irrational numbers. So we have a contradiction, and so our supposition that Z is an open set in the topology is false. Therefore, Z is not an open set in the Euclidean topology on R. And this is what we were required to prove. This video has been about proof by contradiction, which is also known as indirect proof, We shall now say a few words about why some mathematicians and some logicians prefer to avoid its use whenever possible. Proof by contradiction relies on the following axiom: the axiom of the excluded middle, which says that for any proposition, either the proposition is true or its negation is true. While this axiom may seem self-evident, not everyone is willing and happy to add it to their axiom system. The axiom of the excluded middle says that for each proposition there are only two possible values, T for true and F for false. For convenience, we can assign the numerical value 1 to T and 0 to F. However, 2,500 years ago, the Greek philosopher Plato proposed what was essentially a three-value logic system, in which the axiom of the excluded middle would be false. In 1920, Vukovic formalized the three-value logic system. In his system, there are T, F, and possible. The numerical values assigned to these are respectively 1, 0, and some number between 0 and 1, for example, a half. In 1965, Zeta introduced the notion of an infinite value logic system in his seminal work on fuzzy sets. The values in his logic system are in fact all numbers in the interval 0, 1. In usual set theory, we are used to the idea that either an element X is a member of a set S, or X doesn't belong to S. This is in contrast with what happens for fuzzy sets. To define a fuzzy set, we let X be any set. Then a fuzzy set is a pair, XP, where P is a mapping of X into 0, 1. We can think of P of X as being the probability that a point X is in the set X, or, better still, as the degree of membership of X in the set X. In classical set theory, P of X would be 0 or 1, but in fuzzy set theory, P of X can take on any value between 0 and 1. We may think that this has no relevance to the real world, but it is definitely relevant to the area of physics called quantum mechanics. Fuzzy logic has in fact turned out to have many very practical applications, and in particular in control theory. In 1985, Yasunobu and Miyamoto of Hitachi demonstrated the feasibility of fuzzy control systems. Their ideas were adopted, and fuzzy systems were used to control accelerating, braking, and stopping on the Sendai Railway just 2 years later. Today, fuzzy logic is used in cameras, washing machines, air conditioners, and refrigerators. Finally, I mention another concern some mathematicians have. It is that proof by contradiction often allows us to prove the existence of something we're interested in, but does not actually tell us how to construct that thing. For example, We use proof by contradiction to prove that there exists an infinite number of prime numbers. But that proof did not tell us how to construct an infinite number of prime numbers. Constructivist mathematics says that it is necessary to find or construct a mathematical object to prove that it exists. However, most mathematicians are not constructivists and are happy to accept and use the axiom of the excluded middle and proof by contradiction. Indeed, proof by contradiction is regarded as a very important method to have at our disposal. I hope you found this video helpful and you now understand the method proof by contradiction. However, writing proofs is best learnt by doing proofs yourself. So make sure that you do lots of exercises from my book. Thank you.